So I'm going to be talking about dark matter physics in simulations. And so I'm going to start with this question of what makes up the universe. And I know that you all have seen this figure before from Planck. And so all of the talks that we've heard about so far are some fraction of this ordinary matter, or what's called baryonic matter in the astrophysical community. But what I'm going to spend my time talking about is this larger part of the matter in the universe, so 85% of the matter, not the matter and energy, dark matter. And so first, I'm just going to start by introducing cold dark matter, which in the astrophysical community is largely considered to be sort of the standard dark matter model. And so this cold dark matter only interacts with itself and standard model particles through gravity. And it does a really good job on large scales. So scales above about a megaparsec, and that's what I'm showing here on the right-hand side. So this is the matter power spectrum inferred through cosmological measurements ranging from the cosmic microwave background, that's the green points, to the Lyman alpha forest, that's the red data. And then the red line shows the best fit to a lambda SIDM cosmology for a simplified 5-parameter model, assuming a flat spatial geometry and a scale invariant primordial spectrum. Okay, so even though cold dark matter does a good job on large scales, so scales above a megaparsec, there have been a number of observations that show that cold dark matter alone can't solve all of the problems at sort of galactic scales, so few KPC scales. And so here is everybody's favorite small scale problem, which many of you I know have worked on in this room. But for those who aren't familiar, on the left-hand side, I'm showing a dark matter density profile. So that's dark matter density. On the y-axis is a function of radius from the center of the galaxy on the x-axis. And this is data from rotation curves. And what you see is that the rotation curves are sort of have these flat density profiles, whereas what dark matter only simulations is predicting are these more steep dark matter profiles in the central regions. And so here I have a sort of cartoonized version of this, just to introduce some language that I'll use. So the inner halo is often parameterized as a power law, so just R to the alpha. And in CDM theory, they produce what are called known as cusps, and those have an alpha of about -1, whereas what we're seeing from these observations in dwarfs is more chord-like profiles, which have alpha of closer to 0. And so these cusp profiles are predicted by the standard CDM-only simulations, so not including baryons. However, chord dark matter profiles are what we're seeming to observe in nature in these dwarf galaxies. Okay. So in the literature, there are a number of potential solutions that have been proposed. The first is non-standard dark matter. Maybe something is happening with the dark matter other than just interactions through gravity. We know that the baryonic matter, so that small sliver in the mass energy pie chart from Planck, we know that there's all kinds of complicated physics in the baryonic physics. That's why we can see each other. There's electromagnetism. That's why there's chemistry from the strong force. So maybe there's something equally interesting happening in the dark matter sector. And the second thing is baryonic physics. Okay, so I'll start with the first potential solution, which is non-standard dark matter. Okay, and so to help alleviate issues on small scales, any non-standard dark matter model needs to be able to relax dark matter densities on galactic scales. That's one thing that it needs to do. And the second thing that it needs to do is I showed that CDM does a really good job on these large scales, so megaparsec scales. And so any non-standard dark matter model needs to preserve the success of lambda CDM at large scales. Okay, and so this is where one such model comes in. So this is self-interacting dark matter. And this was proposed in the seminal paper by Spergel and Steinhardt in 2000. And they proposed that if you have a dark matter that has a mean free path ranging from about a kiloparsec to a megaparsec, you can naturally impact galaxies on KPC scales while still preserving the large scale success of CDM. And so the cross sections that they proposed were somewhere between 10 to the -1 to 10 to the 2 centimeters squared per gram, where a centimeter squared per gram is approximately a barn per GeV. That's similar to neutron-neutron scattering. And so you can get this from hard short-range interactions like neutron-neutron scatterings at low energies. And so these are sort of 2-to-2 interactions, and these are the interactions that are often considered in simulations. Or you can get self-interactions from soft long-range interactions mediated by the exchange of a light or massless particle. And I won't talk about this, but if you do want to know more about this, this can produce many, many scatterings. I recently submitted a paper for publication with Matt McQuinn on the astrophysical plasma instabilities induced by long-range interacting dark matter. Okay, so now that I'm done with my shameless plug, I will tell you a little bit about how SIDM creates cores. And so it's kind of simple. So SIDM, basically, now that you have these interactions between dark matter particles, it introduces a way for you to transfer energy amongst the dark matter particles. And so here on the left-hand side, I'm again showing this dark matter density profile, and the different colors are the different models. So the black is CDM, and then the colors are various SIDM models with different cross sections ranging from 3 to 50 centimeters squared per gram. And this is the most massive halo in this storm suite that Jillian discussed yesterday. So this is a zoomed dwarf volume. And so to think about the physics, let's think a little bit about the velocity dispersion, which I have on the right as a function of radius from the center of the galaxy. And so what happens is, because you have this way to exchange energy, the inner halo becomes thermalized by the outer halo when these particles can self-interact, and you are pushing towards an isothermal profile. Okay. So that's the small scales. You're producing cores on small scales with this self-interaction. And now let's think about the large scales. So this is a cartoon picture showing that lambda SIDM, excuse me, inherits the large scale success of lambda CDM. So here I'm showing volume from Romulus 8, and this is CDM on the left, and on the right is SIDM with a cross section of 10 centimeters squared per gram. And if you look at them and you're like, oh, they look the same, they're indistinguishable. Here's another way that you can sort of see this, a simple way to see this. So this is again storm at the top, and then these are the runs. So these are density maps, dark matter density maps with the various cross sections. And over here on the right, I'm showing an integrated mass function. And you see that the integrated mass functions between CDM and the various SIDM runs are consistent. Okay, so self-interacting dark matter seems promising as a solution to the Core-Cusp problem. Now, what about baryonic physics? Okay, so here on the left-hand side, I'm showing a simulation that came from the N-body shop. This is Ferah et al. In 2015. And this is kind of a complicated figure, so let me just try to piece it apart a little bit. So these two dotted lines are CDM-only simulations, and so you're seeing that same thing that you were seeing before from NFW profiles. So these are sort of cuspy-like profiles. And then these dashed lines are SIDM-only simulations, so you're getting more chord-like profiles. Now, in this halo, H516, this is a larger mass halo that has a stellar mass greater than 10 to the 9 solar masses. And what you see in those halos is when you include baryons, and in particular bursty star formation, so you have a high density threshold for star formation, you produce cores. However, at this lower mass scale, so this is a halo that has a stellar mass less than 10 to the 9 solar masses, you are still producing, even with the baryons, you're still producing a slightly more cuspy profile. Okay, so then on the right-hand side, this is from Vogelsberger 2014. And instead of implementing a bursty star formation, they have a smooth star formation. And so low density threshold for star formation. and the runs with or without baryons seem to be identical. So the black is CDM and the blue is SIDM, and the dotted is dark matter only, whereas the solid are with baryons, and you see no difference when you include the baryons when you have a smooth star formation or low density threshold for star formation. So if you have bursty star formation, yes, you get cores. If you have smooth star formation, no, you don't. Okay, so baryonic physics can be a solution if star formation is bursty. And so the community sort of went away a little bit from thinking about self-interacting dark matter once this sort of feedback was showed to also produce cores. But there is this new sort of problem that has been cropping up in the community, which is the diversity of rotation curves, or the core and cusp problem. So here I'm showing Spitzer rotation curve data, and CDM predicts nearly identical rotation curves for similar maximum circular velocities. So that's the black with the gray lines. Whereas observations are showing diversity in the dwarf rotation curves for a fixed maximum circular velocity, in this case, Vmax of about 80 kilometers per second. So this curve is largely consistent with the prediction from CDM. However, this is a very fast rising rotation curve. And so this is something that's seeming like it's steeper than NFW. And so maybe this is due to like adiabatic contraction. And then here you have these galaxies that have more slowly rising circular velocities. And so this is this mass deficit. This is these more cord-like galaxies. Okay, so what's really interesting is these type of objects. And so I said before, you could potentially get them from adiabatic contraction. And so in the next figure that I'm going to show you, we're going to look at that explicitly. So there are a few quantities. So there's this fiducial radius. And at this fiducial radius, they define this quantity called eta rot in this Santos 2020 paper, where they look at the velocity, the circular velocity at this fiducial radius divided by the maximum circular velocity. And so this is a measure of how fast or slow the inner circular velocity rises. And eta bar, which is the baryonic velocity divided by the total fiducial velocity. And this is a proxy for the amount of baryons in the center region at this fixed fiducial radius. Okay, so this plot has a lot going on, so let me piece it apart a little bit. So this is data. So all of the points here are data, and they're colored by the log of the maximum circular velocity, which is a proxy for mass of the system. This line here is NFW, is the NFW prediction at that fiducial radius. These objects below this line, so so on the y-axis I have the n rot, which is the proxy for how fast or slow the rotation curve is rising, and on the x-axis you have eta bar, which is the proxy for the baryonic content in the central region. So these galaxies down here are the cores, and these objects up here are the objects that rise faster than NFW, so those are steeper than NFW. I'll come back to these points because these are objects that are steeper than NFW but have small baryon content in the central region, so they can't be produced from something like adiabatic contraction. Okay, so this is a simulation with low density threshold for star formation, so it can't make cores. So you see that you're not producing cores here. This is a simulation from Eagle that has a high density threshold for star formation, so it can make cores. So you are seeing these objects down here that are consistent with the core, but they have low mass resolution, so you're not resolving small objects. And then here, this is a Niehaus simulation. So you also have this high density threshold for star formation. So again, you can make these chord objects, and you have a higher mass resolution. So you're also able to resolve smaller objects. And so these points here, these are the points that have a higher baryonic content in the central region. and you are able to produce these objects. These objects are something like a Milky Way and have large central densities and of baryonic buildup. And so you are getting something steeper than NFW from adiabatic contraction. However, these points, they have pretty small baryonic content. And so you can't get these from just including baryons and having adiabatic contraction. And these points are a real problem for even the CDM plus baryon paradigm. Okay, so as I just said, these objects are hard to produce in CDM plus baryon simulations. However, SIDM may offer a unique solution mechanism for this, which is gravel thermal collapse. So this gravel thermal collapse is similar to what we see in globular clusters, which will take the NFW profile and make it even steeper, because with SIDM you can produce a negative heat capacity. And Carton will talk more explicitly about this in his talk. Okay, so what are we doing in the N-body shop to try to think about this problem? Well, I'm going to just quickly talk about constraints on SIDM so that we can have a more well-motivated cross-section going forward rather than just a constant cross-section. And so in particular, observations at different mass scales suggest that the SIDM cross-section should be velocity dependent. And so here on the right-hand side, I'm showing the cross-section velocity weighted by mass, and then by the average velocity. And you see here for these cluster scales, so the lines are constant cross sections, that the clusters should be sitting around 0.1 centimeters squared per gram, whereas dwarfs should have higher cross sections. And we know that we need higher cross sections to be able to induce that gravel thermal collapse. And so there have been some recent work by a number of people in the community that have showed in particular that a cross section of 3 centimeters squared per gram can reproduce the full range of diversity curves where diversity is maximized, which is around 80 kilometers per second. And so we introduced this new SIDM velocity dependent cross section, which is based on this paper, which was done in collaboration with Sean Toulin, who is our collaborator on this work and has helped us to create this very crazy looking velocity dependent cross section, which also includes resonances. And but the main takeaways are that at sort of cluster scales, you're getting the correct cross section, and then around where you want diversity to be maximized, you're getting cross sections of about 3 centimeters squared per gram. And so this has been implemented into Chang'e. Okay, so now I'm going to switch gears a little bit for the last 6 minutes and talk about black holes in SIDM. So seeding black holes with SIDM. So this idea of this gravel thermal collapse has become very interesting to the SIDM community because it may be a way to actually produce black hole seeds and help with these really supermassive black holes of 10 to the 9 that exist when the universe is only 6% of its current age. So these are those really big ones that we have a hard time growing from other seeding mechanisms, and just having accretion, Eddington accretion. Yes, sorry, Eddington accretion. And so this is an interesting avenue that people are exploring, although it's pretty complicated to get this to work. But a few years ago, I did something a little bit different. So I used hydrodynamic simulations, and so these are the GM simulations. And these were presented yesterday by Nicole Sanchez as well. So this is a series of Milky Way galaxies, and they have similar initial conditions using genetic, which I guess Andrew gave a tutorial on earlier this week. And so we run with CDM and then an SIDM cross-section of 1 centimeter squared per gram and 2 different IC sets. So this purple represents one IC set and the orange represents another. And so this is run with Chang'e in a fully cosmological context, zoom within a 50 megaparsec box, and a mass resolution of 10 to the 5, excuse me, solar masses for gas and stars, gas and dark matter. You have Stinson feedback and Tremel black hole physics, which we saw yesterday, maybe has some shortcomings. So maybe, you know, we'll do this study again with newer galaxies, more robust study coming up. So this is, of course, all of the physics that was discussed that's in Romulus. So these are simulations that are consistent with Romulus, which is zooms. Okay, and so you have a seed mass black hole of 10 to the 6th, and again, this forms in dense, low metallicity gas. That's important. And the other thing that's important is that you have this dynamical friction, so you can sort of trace the orbits of the black holes. Okay, so I guess I'll show this because I think I have a bit of time. So on the left-hand side is GM3, and on the right-hand side is GM3 with SIDM, and the red is feedback. And what you notice throughout the course of the movie is that the feedback looks like it's stronger in the GM3 run compared to in the GM3 run with SIDM. And in particular, there's this very large event where you can really see this large difference here. There's this really huge accretion event in this GM3 galaxy that you're not seeing in this GM3 SIDM run, or at least it's not as significant. Okay, and so why is this happening? Well, in this 2020 paper and even before this, in Decentio 2017, we have some hints that the black holes maybe behave differently in CDM versus SIDM. And so in particular, we find in my 2020 paper that the SIDM delays supermassive black hole growth by mergers by billions of years. And so this has two things happening. So the first thing is that mergers depend on the dynamical friction. And so if you have decreased densities, you have longer dynamical friction time. So this is, Shijing was asking Jillian about this yesterday. And so here you're sort of seeing that effect. So this is the black hole distance from the center of its host galaxy. On the y-axis is a function of the stellar mass on the x-axis. And you see in CDM that the black holes are sitting, for the most part, at the center of their galaxies because they have that more cuspy-like profile. Whereas SIDM, because of the cores and this decreased density and increased longer dynamical friction times, these black holes are sort of wandering for longer. So the other thing is the number of black hole formation sites that will also affect the merger rate. And in our 2020 paper, we found that SIDM produced fewer total black holes, which will also lead to fewer mergers. And that's what I'm showing here on the right-hand side. So this is the black hole mass from mergers divided by the total black hole mass as a function of cosmic time. SIDM is the dotted, and then the colors are the two different initial condition sets. And the solid is CDM, and you see that there is this delay between when you get the first mergers in CDM compared to when you get the first mergers in SIDM. And this delay is billions of years long. And so, of course, this affects, this delays the growth of the black hole. And so you're not seeing in that video, you're not seeing as effective accretion because the accretion goes proportional to the black hole mass. And so that's why you're seeing those differences in that movie. Okay, so I have 44 seconds, so perfect. Here's my summary. Self-interacting dark matter produces rich physics on galactic scales while preserving the large-scale success, and is in agreement with a number of observations. And baryons, yes, they are important to galaxy formation. We all know that. But they have yet to show that they can solve all of the small-scale problems, and in particular, this diversity of rotation curves, which we're working on. And so to do this, I have this new SIDM velocity dependent cross section, which agrees with observations at cluster scales and which should maximize the production of diversity at dwarf scales. And Tom and I also worked on implementing variable time stepping into Changa, so that when you do get gravel thermal collapse, you're going to get these really large probabilities because the probability of interaction is proportional to how much dark matter is around. And so if you have gravel thermal catastrophe, your densities are really large, and so your interaction rate is going to go up. And so you're going to need to be able to take proper time steps to account for all of the SIDM scatterings. Okay, and so the phases of the dark matter density profile in lambda SIDM, so NFW to core to gravel thermal collapse, may offer new ways for us to probe black holes. And in particular, we showed, at least in sort of these now, I guess, older simulations, that SIDM can delay supermassive black hole growth by billions of years compared to in CDM. And this can potentially be probed by LISA, which is definitely something of interest. That's everything. Thank you.
Okay, go ahead.
Wonderful talk. This is Jillian Bellaveri. Hi. I am excited about this gravel thermal collapse thing. So your prior work that showed that the black holes evolve differently in SIDM, I assume that the black hole seeds formed in the same way in those simulations, like whatever the prescription was, they formed the same,
Yeah,
or were
exactly.
they seeded the same?
It's direct collapse.
Yeah, and so if gravel thermal collapse is a way to make seed black holes, those results might change a little bit. Do you have any idea on how they would?
You might end up producing, instead of producing fewer mergers, you might end up producing more, maybe, if you can get it right. But actually, it's pretty hard to do this gravel thermal collapse and produce these black hole seeds. So actually, let me just start there. So in particular, they are looking at systems that are relatively rare. So these big halos, these like Milky Way mass halos at Z equals 6 or 7. And they also show that in order for you to get this gravel thermal collapse with a cross-section of 1 centimeter squared per gram, which is generous at this mass scale, that you also need the addition of very centrally dense very compact baryonic potential. Right. And so it may only happen for some halos, and I'm not sure if it would happen for at the Milky Way mass scale.
Got it. Thank you.
Okay, we do have one question on Zoom from Ben Keller. He asks, is the way SIDM is treated in the code more or less the same as hydrodynamics, just with a weird equation of state?
So the way that it is done is you have the particles, and of course, like, they're not actually particles. So you're doing these 2-to-2 scatterings, but of course, like you mentioned yesterday, Ben, we don't have the resolution to actually model one-to-one interactions of the actual mass scale that these 2-to-2 interactions would be happening at. And so the way that it happens is that you're just assuming that each dark matter particle is representing some phase space. And so you're doing some interactions in the phase space of the SIDM. I'm not sure exactly how it compares to what is done with gas, but I wouldn't say that it's necessarily with a weird equation state.
Okay, go ahead.
Fantastic talk. I have a ton of questions, but I'll ask this one. If SIDM produces weaker episodes of AGN feedback, have you looked at how this affects the CGM and the galaxies?
Yes, I have, and I am looking at that now, and a paper is coming very soon.
Exciting. I'll leave the other ones for later.
Okay, maybe one more quick question. I think over there you had your hand first.
Hi, this is Nicole Sanchez. Really excellent talk. I love seeing the side-by-side movie. So cool. And so you mentioned that differences in the mass scale are resulting in the difference in the feedback. Can you speak to how closely the accretion rates track each other through time?
In CDM versus SIDM?
Yes, yeah.
Yeah, so the accretion rates are much lower in SIDM during the first 6 gigayears of evolution compared to their CDM counterparts. And then later on, when the black hole eventually catches up, because you eventually get these delayed mergers, and so now you have sort of similar masses in the black hole, and you know that the black hole accretion rate is going proportional to the black hole mass squared, and so at later times the accretion rate is actually more similar.
Very cool. Thank you.
That's all we have time for. So let's thank Akaxia one more time.
So today, I am going to talk to you about measuring dark matter physics with cosmological simulations. But first, I want to point out that my contact information is going to change very soon. And I don't know when my email address will expire, so I have a new email address listed on the slide. And since I'm old and getting senior-ish, I can't wander away, right? My talk is actually going to address something happening in the particle physics community right now. And this process is called snowmass. And snowmass is essentially the particle physics equivalent to the astrodecadal survey. And in the process of going through this, I was asked, along with Arka Banerjee and Annika Peter, to put together a white paper that addresses the role of cosmological simulations in constraining dark matter physics. So I have memes, and the memes have a point. And I think the point is really well encapsulated in this sentence from our paper, which I'm calling the takeaway from this talk. And that is that a successful program to extract dark matter physics from observations depends critically on a really robust theoretical framework. And the beauty of simulations is that they can mediate those two communities, the particle community and the astro community. And so in the last few years, in astronomy, people like me have been like, astrophysical constraints on dark matter, right? And in the particle community, particle physicists, in light of direct detection only giving limits, have started to look towards astronomy. And we've been kind of working in parallel when things should really look like this, okay? Particle theory and astronomy need to be working together, and simulations are the way to do it, okay? And so in the process of writing this paper, what we did is we identified particular needs that need to happen in the next decade in order for simulations to connect the microphysics, the particle theory, to the macrophysics, the astrophysical observation that could constrain dark matter. And so I don't want you to get too caught up in this ginormous picture from the paper, but what I love about this diagram is that it shows us all the different models that people have implemented in simulations. It connects it to the particle theory driving that model, and it also addresses some of the challenges that we are currently facing. And what I also love is that we did not forget my favorite part, the baryons, right? And so understanding the baryons, doing code comparison tests like Agora are definitely a necessity. So I wanted to go through some of these needs. And so as I have emphasized, we need close collaboration between us as a simulation community and the particle physicists. And we need to be working together to develop the algorithms so that they accurately represent the dark matter physics. And we need to do this across different codes so we can validate our results with code comparison tests. So like we've been validating the baryonic physics with things like Agora, we need to do something similar with the dark matter. And baryons are important, as Akaxia told us, right? Some of the solutions to some of these dark matter problems can be the baryons. And so we need these simulations to be fully hydro, and we need to think carefully about our subgrid models and the role of resolution in our subgrid models. And then we need to take our outputs and put them in a space where an observer will actually understand us, right? And so what that means is that we need to come up with efficient ways to realize these observables so we can infer dark matter properties. And we need to give the observers exactly what to look for, in particular in light of all these amazing observatories coming online in the next decade. And so I've put the needs back up there. And what I wanted to talk about next was what work the N-Body Shop is doing to specifically facilitate these needs. So Akaxia's talk was wonderful because she started telling us about what Chang'e is doing with self-interacting dark matter. And Carton is going to, I don't know if he's virtual or here, going to tell us some more. And so I will leave it to them to show some really incredible results. But in this white paper, what we also kind of designed was a bit of a roadmap that we need to follow in order to address the needs that I outlined. And so this, talks about deriving the appropriate initial conditions, analyzing those outputs, translating them into an observable space, modeling them, and efficiently comparing it to data. I also wanted to advertise selfishly that Annika, me, Kimbody, and Vera Glusevich just had a KITP program accepted for summer 2024, where our proposal essentially was to bring all these communities together to start working on addressing these needs in light of Rubin, Roman, and JWST. So stay tuned for that. I'm super excited. It took multiple submissions to get this past the KITP folks, so I'm stoked about this. And I also wanted to show the incredible work that our collaboration has done in addressing these needs. So each of the needs has a color, and then this is a non-exhaustive, everybody is not on here, I did my best, list color-coded by what needs those specific papers address. And what you can see is that there's a lot of colors up there. We're doing a damn good job. Hey, yeah? You're all in the collaboration. The answer is yes, right? And so you can see that the N-Body Shop has definitely been leading in terms of these fully hydrodynamic simulations, pushing resolution, but in particular, we are really strong in these apples to apples comparisons with observations. So translating into observer space and looking for observables. And we've been doing this for a decade plus. But what you might also note is that there are particular colors that are less representative up here, right? And so in a collaboration meeting like this, I put this up because with snowmass going on, with us setting the priorities for the next decade in dark matter physics, it's important for us to think about where we could be doing better. And KITP would be a great place to, start to think about these things. All right, so I also wanted to show some science that my group has been doing in collaboration with Akaxia, Allison, my grad students, my undergrads. And in particular, I love small things. I love dwarf galaxies. And dwarf galaxies are where the challenges lie. We just heard about this from Akaxia. And they're very important to understand because there's going to be an explosion in finding them in the next decade, okay? And so Akaxia talked about some of the small scale crises for dark matter, and I borrowed this scorecard from Allison. And cold dark matter with baryons can solve things, but so can some alternative dark matter models, which is why we are studying SIDM in Chang'e. And in particular, in collaboration with Akaxia, using her fantastic new velocity dependence, we are looking into the shapes of dwarf galaxies as an indicator of SIDM versus CDM, because those interactions in the centers of these dwarf galaxies will sphericalize the shape of the galaxy in the dark matter halo towards the center, as is shown in this picture by my grad student, Jordan. And so I wanted to advertise that we are running a series of runs, some of which are a subsample of Marvel and some of which will be brand new runs with this velocity dependent cross section, which will be for the dark matter only runs, the Kamala dark runs, and then with baryons, the Kamala runs, keeping in light of our theme of women superheroes with also a nod to our first woman vice president. And I want to remind you that the baryons are really important. I wouldn't be me if I didn't shout about baryons. And so if you add baryons to any of these models, right, you can solve all the problems with all the models, right? And so understanding the role of baryons is still really important. So even though I'm looking over my shoulder at dark matter physics, I can't forget about the galaxy formation, right? And so a lot of my students have been using my favorite suite of all time, the Marvel plus the DC Justice League suite, to look at the role of the baryons in some of these small scale problems. So Bianca and Alexi, who are off to graduate school, but were my undergrads, are looking at how bursty star formation affects the formation of cores. And in particular, more massive galaxies tend to have bursty star formation histories throughout all of cosmic time. So they're able to form and maintain cores. However, ultrafaints and smaller dwarf galaxies that don't end up with a core in the time that they were actually forming stars actually have burstier star formation histories than the more massive ones. And now we are looking into this as a function of what type of feedback physics is in the simulation. And so this is really exciting work with the baryons. And then in Marvel, I am also looking at whether we can believe the claims of these dark matter deficient galaxies. And in particular, recently it was proposed that a major merger can separate out the baryons from the dark matter halo a la bullet cluster. And so we were looking at the time of the last major merger in two different groups of dwarfs. The high baryon fraction ones, which in the centers might look very dark matter dominated, and the low baryon fraction ones. And what you can see is the distribution of last major mergers doesn't indicate that this is what's happening in our simulations. And finally, the faint end of the mass function, where galaxies start to go dark, what its form looks like is one of the main constraints people are looking to use for dark matter, because it's going to look different as a function of dark matter model. It turns out that that is very sensitive to your subgrid model. And so we're showing two different star formation recipes and how that affects the faint end of your mass function. And you can see they are not the same. And that also is affected by the scatter in the stellar to halo mass relationship. So you end up with a steeper faint end if you have scatter that grows as a function of halo mass. And so I hope that I've convinced you, one, that my group's doing awesome science and my students are amazing, but also that we need to take a step back as a community and think about how we can combine our knowledge as astronomers with the particle physicists and use simulations as accurate ways of constraining dark matter physics. Thank you.
Okay, any questions?
You're not allowed to ask questions.
I wasn't going to ask a question. I was going to make a comment.
Okay, that's okay.
So just as an even older person, you know, sort of remembering past successes and not so much of sort of astrophysics and particle physics. You know, sort of the warning is sort of Big Bang nuclear synthesis was arguing for 3 neutrino species, and that argument was not made well. And I think they were kind of overselling it, I think, is what happened there. But then the other example is the neutrino mixing from essentially Bacall's simulations of solar nuclear burning. And that was amazing, right? That he was very careful with his simulations and had this amazing result that was only later sort of drove the particle physics to look at neutrino mixing models. So there's have to be cautious, but there's potential for amazing results. So that's my comment.
Yeah, I'm okay with the comment.
Hi, it's Andrew Ponson. I have an actual question, which possibly both to Ferah and also maybe slightly to Akaxia as well, because you've both highlighted this diversity issue in dwarf rotation curves, which I think is super interesting. But Kyle Oman has been saying quite strongly that it's like an observational bias effect to do with non-circular motions and blah, 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 blah. And I find it really hard to figure out whether to believe him or not. I mean, Kyle goes a very long way actually and says he doesn't believe there's evidence for cores in the data at all, which is, I mean, that's like going back to the debates of the 90s, right? So what are your thoughts on this? How seriously should we take diversity? Is it really there or is it not?
I think Akaxia answers this question better than I can. Yeah.
All right, Allison Brooks jumping in. Yeah, no, actually, I think some of Kyle's recent work is amazing. I think when it comes down to it, nobody has shown, no simulator, nobody in this room, nobody in any group has shown that they can make cores and solve the diversity problem, right? And Kyle has really emphasized that really we can't make the most dense things in any simulation so far that also makes cores. And that is a serious problem for us and a challenge that we need to try to address and understand. So I think we should take it very seriously. It really throws my my understanding of core creation into doubt.
But Kyle blames the observation.
Kyle has shown that you can reproduce the full scatter just by doing mock observations. So yeah, I understand why he believes that. I feel like, the observers, like historically, right, they met that challenge of like, all right, you need higher resolution, we'll get finer resolution and show you that there's still cores that are there, right? I think there's got to be some sort of smoking gun galaxies where you can say this has to be a core, but until somebody points that out to me, I don't know what galaxy that is off the top of my head. So yeah, I don't know.
So I'm Parkinson. I'm a grad student from the Ohio State University, working with Professor Annika Peter. And my topic today will be focusing on the evolution of self-interacting dark matter subhalos. And so my talk today is mostly based on this paper from last year. This is the archive number and my awesome collaborators. Okay, so since Akaxia has covered a lot of materials on SIDM, so I'll skip part of the introduction and directly jump to the halo phenomenology of SIDM, namely the core and core collapse phases. So as we know that starting on top of cold dark matter, if we turn on the self-interaction or two-body scattering between dark matter particles, effectively it allows for the exchange of momentum among dark matter particles in a more efficient way. So, for example, if we start from an NFW halo in this orange line, the upper panel being its density profile, and the lower panel being its velocity dispersion profile, or in other words, the temperature profile. If we suddenly turn on the self-interaction, there will be both heat inflow and heat outflow from this temperature peak. And this heat inflow, as Akaxia has mentioned, will lead to the thermal equilibrium in the core, in the central part, and leads to the core formation naturally. But that's not the end of the story yet. There is also the second phase, which is induced by this slowly but continuously going heat outflow to the outskirts. This is because of the so-called negative heat capacity of the self-gravitating system. This process is slow but endless, and eventually will lead to the core collapse of the halo. So think about this scenario. So if a dark matter particle coming from the hot inner part scatters off another colder dark matter particle from the outskirts, the inner particle loses heat to the outer particle because of the two-body scattering. It cannot remain at its current orbit. It will infall, where it becomes even hotter than before. That's what we mean by the negative heat capacity. So you lose heat and you become even hotter than before eventually. And that actually makes this negative temperature gradient more and more negative than before. And so this core collapse process is a self-accelerating and runaway process. So yeah. So why is this two-phase phenomenology interesting? So So because it can provide possible answers to first, in principle, providing possible answers to like the diversity problem of the rotation curves in dwarf galaxies. I have a different figure of the diversity here. So from this Hayashi paper back at 2020, the two bands here are the inner slope of dark matter halos from Nihal and Ferah, which are two hydrodynamical simulations, while the dots here are from actually observed Milky Way dwarf satellites. So as you can see, even by including baryons and hydrodynamical simulations, they cannot completely answer the diversity of these observed Milky Way dwarf satellites. The second thing that SIDM can provide possible answer to is, like Akaxia talked about, the seeding supermassive black holes by this core-Cusp, especially those supermassive black holes that has a apparent low Addison equation rate, so may not be explained by direct collapse of gas. And an even good thing of SIDM is that it can be easily constrained. People already have put some strong constraints on the galaxies and above scale, mostly on the core phase. But with upcoming substructure lensing surveys, we may also be able to put constraints on the low velocity and namely smaller subhalos in the near future. Okay, so about our work, so we know that simulating SIDM subhalos can be expensive, first because simulating subhalos itself can be expensive, especially if you want to go down to subhalos of 10 to the 6 to meet with the upcoming surveys. Like if you want to resolve subhalos down to 10 to the 6, well, your whole system is about 10 to the 13, you are wasting a lot of power in simulating the host in particle form. And on the other hand, simulating core collapsing scenarios can be itself very time consuming, because you generally need more and more time step when you're having a density region that is growing, right? You want to make sure the self-interaction of physics is resolved correctly in a high density region. So we are motivated to build or develop this hybrid method to focus on subhalos. By hybrid, we mean that we track the evolution of subhalos with unbodied particles for high fidelity, while we replace the host halo with analytical treatment so that we don't need to waste our computational power there. Okay, so you see that we're doing idealized simulation here with an isolated host in a non-cosmological context, and we inject subhalos in it and study its evolution over time. And we're using a ripple as our simulation code. Okay, so by using this hybrid approach, we need to make sure that we capture all the interactions between this analytic host and the embodied subhalo correctly. So what effects that the host have on the subhalo? So first, of course, naturally, we have the tidal or gravitational effect, which is straightforward to implement. It's just an external static. Well, it can be time involving, but currently we only have static potential. And next, because it is SIDM instead of CDM, we also have the self-interaction between a pair of particles, one coming from the subhalo and another coming from the host halo. And this matters because there's a velocity gap between the host particle and the subhalo particle relative to the subhalo set. This matters because after this two-body scattering, there will be a great velocity gain on the subhalo particle that will possibly and even very likely lead to the unbonding of the subhalo particle from the subhalo. And this could even potentially disrupt the core-Cusp. So this is some details about how we implement this evaporation effect. I will not go into details of it. It's just that first step, we evaluate the probability of each subhalo particle, basically the probability whether it will scatter off a host particle and have this evaporation event. This is just proportional to the local host particle density and the mean difference between the velocity dispersion of the host particle and this specific subhalo particle. And then we do the redistribution if it scatters off. Okay. We validate our method using this movie here out later. The upper panel being the density profile of the subhalo, and the lower panel being the integral version of that. So it's an enclosed mass profile. There are 3 halos here with different initial concentrations. And okay, so we'll be focusing on this scatter dot versus the dashed or dashed dotted line, which is validation of our method. And also, I'd like to highlight the difference of including the evaporation effect or not in the dotted versus dashed line. Okay, so here we go. As a spoiler, the blue for C equals 8 decades will have core-collapse happening at about 2 gigayears. So we already see the difference of including core-collapse, including evaporation or not. And right before, okay, so this dotted halo is core-collapsing, so we have to terminate it here, so it's gone. But the other blue one still remains. This tells us really the difference between including the evaporation effect or not in the evolution of subhalo. And maybe I can accelerate this a little bit. So our method in the dashed line shows remarkably good agreement with the live host simulation in the scatter dots. Okay, so this is the validation of our method. And before we dive into the results part of our work, a little bit preview of how we studied this. So we try to break down the relevant physics processes of the relevant of driving the subhalo evolution into 3 parts, 3 cooling and heating terms. So the first one is the internal heat transfer within the subhalo. So from the perspective of the subhalo core, there's heat outflow from it. So it's a cooling term acting on the core. And there's tidal effects. So tidal stripping does not directly have a heating or cooling term on the core. Instead it truncates the density distribution. So it has indirect effects on the first cooling term. But there's also tidal heating, which is the work done by the tidal force, which is not strong enough to strip away a particle from the subhalo, but it still does work. So it's heating term on the core. And also there's evaporation. There's whole subhalo evaporation, which injects kinetic energy into subhalo, so it's also a heating term. So here we show our main result. The first panel being the central density as a function of time of the subhalo. So we have 4 subhalos here. The second panel being the orbital distance, so from epicenter to pericenter. And the 3 lower panels are the heating and cooling terms respectively. So if we focus on this thick green line first, so there are 4 subhalos here with a combination of 2 cross sections of SIDM and 2 initial concentrations. If we look at this thick green line first, it starts from FW, have 4 formations first in a short period of time, and then core collapses normally as expected. But another similar subhalo with slightly lower initial concentration of 75 starts from NFW for formation first, but its core collapse process goes slower because of its lower initial concentration, so that it cannot reach core collapse before the first pericenter encounter, so that evaporation comes in and disrupts its core collapse process, so that you can see its central density decreases by about 2 orders of magnitude in this period of time and can never come back again. Similar things happen to this pair of subhalos, but with slightly lower cross section of 6 centimeters square per gram. The thicker line, it starts from NFW, has core formation, tries to core collapse, being disrupted, but it's not forever destroyed, so that it has a second chance to come back later and finally core collapses. And similar scenario applies to this C equals 75 orange line. It's just that it has to experience 2 ups and downs before it eventually core collapses. Okay, so with this, periodic ups and downs, it actually tells us that SIDM cosmology actually could admit a large diversity of subhalo central densities. You can see these ups and downs here. And that could provide a potential answer to the previously mentioned diversity problem. And our primary conclusion in comparing these heating and cooling rates is that the subhalo central density grows if and only if there's night cooling outweighs the night heating by correlating the evolution of the central density versus the other terms. Okay. And also another thing we learned from here is that the evolution of an SIDM subhalo is highly sensitive to its parameter, its initial parameter, as we can see in the comparison of the CA equals 675 versus C equals 888. So following that spirit, we're motivated to map out the parameter space in which we can see where the boundary above which the subhalos can eventually core-cusp. So here the x-axis being the cross-section of the SIDM, y-axis being the critical initial concentration, and different color lines meaning the different ellipticities of the orbits. So above these lines are the allowed regions for core-cusp for subhalos. But we know that cosmologically, you don't have such crazily high concentrations. Cosmologically, for halos of this mass, the typical concentration is about 20 to 25. So this basically tells us in SIDM with constant cross-section, you wouldn't expect core-cusp to happen. And any observed ultra-compact dark matter substructure would instead favor additional degree of freedom of SIDM. Okay, so here's my takeaway page. So we know that core-cusp of subhalos or halos is basically a unique imprint for SIDM. And with SIDM, you could possibly see a large diversity of subhalo central density and provide possible answers to small-scale issues of CDM. And we made a fast hybrid method, allowing us to study basically arbitrarily small subhalos. And yeah, that concludes my talk here, and I'm happy to take questions.
Okay, we're a little bit behind time, so I can take one very quick question. Go ahead.
Amazing talk. This is Ferah Munshi. Am I crazy, which is quite possible? What I'm hearing in your kind of the previous slide that we just had up about the balance between the heating, maybe one more back, that you might be saying that the diversity is environmentally dependent in the sense that the tidal heating and the cooling outflows because of the SIDM have to balance in a particular way to get the diversity that you're seeing.
Yes, at least partially, yes, I would say. So I would put it this way. So we see drastic difference between infilled halos and subhalos, if that's the same with what you just said, the environment dependence.
That's really interesting. Thank you.
Okay, let's thank Carton again, and we'll come back after break.
Thank you.